Okay, welcome back everyone. This is the fourth video in a series that we're making to learn Rust, the programming language Rust, but we're applying it to a specific challenge or a specific application, one which is to process data which is commonly used in astronomy, and that data format is called FITS. And so in the previous videos I've covered a little bit about what FITS is, and on this GitHub repo here, which is going to be in the description below this video, so feel free to check that out. We have a README file that sort of sets up what we're trying to do. And so we're going to cover some more of the basics of Rust, but today we're really going to start thinking more about parsing FITS files. At least we've been able to open them and read them, but we want to start understanding the structure of those files. So we'll be diving into the spec that we looked at last time, which is on the NASA website, and we'll be starting to write code to understand FITS files. So the first thing we want to do is just go back and make sure that our original program still compiles. So we'll do cargo run, and it does. So we get our welcome message here, and we see that it reads a certain number of bytes, and that's great. And for those of you that haven't seen, we're really starting with some basic stuff. So we've done some error handling, we've opened some files, read them in entirety, and we've put those in a vector. So it's not the most efficient way to read files, certainly large files, but it'll get us started. What we want to do is go and think about what FITS structure looks like. And so this was the example FITS file that I had in my project. And we covered this in a bit of detail, but we were looking at the summary view on the right-hand column and just scanning through the file, and we saw some patterns. We saw some simple text data at the top, and then we saw some binary data down in the middle, and we think that's probably an image, given that it's coming from the Hubble Space Telescope, and that takes beautiful images. And then there was this table extension at the bottom, and then there's a bunch of other kind of numeric data at the bottom. And so there is a structure, isn't there? Now, I could just start exploring this and start making assumptions about some of this, but if you look at the text data here at the top, there's an awful lot of information. It looks to sort of be a key value sort of structure. At least there's an equals delimiter, or there's some kind of key value pair separated by equals, and you've got bit picks, and it has a magic number there. I don't know what that means. You've got n-axis and n-axis 1 and 2. Anyway, and there's quite a bit of information in here. And just looking at this, it looks like this header information is going to tell us how to interpret the data in the rest of the file, I'm guessing. And then there's a lot of other metadata in here too. And I'm not sure if we'll need that, but we want to be able to certainly parse it and store it and display it. Okay, so rather than making guesses about this, we're going to go and do the right thing and go back to the FITS documentation, which is on the NASA website, and open the PDF file for the spec that describes what a FITS version 4 file looks like. And so this is the spec. It's a PDF. Last updated 2016. Actually, it was, well, yeah. Anyway, that was the original publication date. And we're going to go through here and just see if we can understand how FITS is organized. So we've got some introductory information here. This looks promising. FITS file organization, absolutely what we want to go through and look at. Some headers, information about the data representation, extensions, time coordinate systems, world coordinate systems, how to handle compressed data. So there's a lot in there. Now, we'll just start with FITS file organization. It sounds like a reasonable place to start. And so I'm going to go through this pretty quickly, but it looks as though FITS is composed of a primary header and data unit called an HDU, and then extensions that are optional, and then other special records that are optional. And so we can see that a FITS file that only has a primary HDU or header and data unit is referred to as a basic FITS file, or a single image FITS. And a fits containing one or more extensions is a multi-extension fits file. Now this is where it gets interesting. So each fits structure has an integral number of fits blocks, which are 2,880 bytes long. And the first HDU shall start with the first fits block of the fits file. And the first fits block of each subsequent fits structure shall be the fits block immediately following the last fits block. Don't you love reading specs? They're so specific and they're trying to be so unambiguous. All right, so the standard neither imposes a limit on the total size or a limit on the size of an individual HDU within a fits file. And it talks about how some systems only support files up to 2 to the power of 32 bytes in size. Anyway, that's fine. So we know that a fits file contains the following structures, which is an HDU, some extensions, and some special records. Now, if we go and look inside an individual fits structure, we can see that each primary, or the primary HDU and every extension HDU, so any of the HDUs, any of the header data unit sections, shall consist of one or more 2,880 byte header block. All right, followed by an optional sequence of data blocks. Okay. So we know that a fits file will consist of an integer number of these blocks. Okay, 2,880 bytes in length. And we know that a header unit also has, so we can basically start thinking about chunking a fits file up into these blocks that are 2,880 bytes long. The header block shall contain only the restricted set of ASCII text characters. Okay. So if we have, so we're just dealing with 8-bit, well, not even 8-bit ASCII. Okay. Right, that's fine. All right, so we've got a little bit of an idea, haven't we? So I think if we go back to our fits file, we can absolutely see that this looks like a header. And my guess is that it's going to be some integer multiple of 2,880 bytes long. And then we see an end, which is interesting. And then we have a bunch of, and we've got white space. And so I guess that's probably, it's probably because the header was less than an integer number. And so I think end must signify the end of the header. And then we've got white space, so a bunch of bytes. And then we begin the data block, I guess. And again, that will probably be, I'm guessing, an integer number of 2880 bytes long. And so that's interesting. I think that will get us a long way today. So, and then we've got all these, I don't know what these are, null characters or something. I have no idea what it's trying to draw here. So, and then we have this table extension thing. Okay, here we go over here. Right, so right up until extension. So it's almost like we're going to be looking for two keywords, which is at least two anyway. One that is end, which signifies the end of the header, and then this extension keyword. And we'll read the spec, but these look like special reserved names or something like that. All right, so let's go back to the spec. So the first header and data unit shall be the primary HDU, which may be followed. So the primary data array is optional. And we know that, okay, so the primary data array could have a 0 length if Naxos and Naxos n. Interesting. So, right. All right. Anyway, so we've got the header. Okay, so now we know a little bit more about the header. So, all right. So there we go. So, so each header contains a series of 80 character keyword records using this restricted ASCII text character set. So I guess, 2880 divided by 80 is 36. And it must contain the end. So the last header block must contain the end keyword. Okay, cool. So so that's why we're seeing this spacing here, right? So we've got basically 80 characters. Yep. If you look here, we can see it's 80 characters long down in here. And so that's why I have all this white space. It's kind of a waste of space, isn't it? But anyway, I guess it makes it simple to parse. So we'll go back and we'll look. So we know a bit about the header. I think we could probably have a go at just naively trying to parse the header out. Then the primary array we'll look at later, but it looks like, yeah. Okay, right. All right. So we'll look at the header later. Sorry, look at the primary data array later. We'll start with the header. So what we'll do is we'll go back to our program, and we will start looping through the data. So we put all of the data, which was basically a vector of unsigned ints, 8-bit ints. We put all of that data into a vector when we read the entire file, and that also returned the number of bytes. We knew how many bytes we had in that file as well, and so that's great. And this is more than enough to store the character set that the fit spec describes. We're not going to be really careful about validating the characters and the character set, but anyway, so we know that there's some special numbers too, don't we? We know that there's this concept of like a sort of a block size. Okay, and so what we'll do is we'll set a couple of constants for now that we'll use in the program. And so the first one will be we'll just call it block size, and it's going to be we'll give it a type of view size for now. Or I don't know, maybe int32 or something like that. And we'll make it 2880 long, and then we'll do another const. We'll call it record size, because that was the record size that it was talking about, and we'll make that 80. Okay, and so these constants will be used when we start looping through the data and looking for data in the file and trying to understand it. Okay, and so in Rust, to define a constant, use the const keyword. I'm using a convention with uppercase letters, and the type is a 32-bit int for now. I don't know if that will work, but I'm sure it's fine. And we've defined these constants that we can use throughout the program, and that's good. So happy about that. Now we're going to do something where we loop through the data file, and to do that, I'm going to use a for loop. Now, I was playing around with this a while ago, and I sort of used I think I just used a standard loop like this, and I was looking for basically I was looking for the end keyword, and so. The problem with that is that if the end keyword's never found, then the program keeps looping forever. So that's obviously pretty stupid. And we could do some stuff to make sure that we're not looping off the end of the file, and we could do some extra bound checking and whatever. But I'm going to try something different. So I'm going to do a more traditional for loop. But what I'm going to do is I'm going to use a tuple here, which is I, underscore, and I is going to be a count, and it's going to represent kind of the index into, if you think about our vector of data, so it's going to represent or look like an index into that vector of data. Underscore is Rust's way of sort of saying, I'm not going to use that variable, so just kind of, I don't care about it, discard it. And so we're going to do a for loop, and we're going to look inside of the fits data vector. So for I underscore in fits data, and then we're going to we're going to create an iterator, and then we're going to on iter, we're going to use something called enumerate. And then after that, we're going to use something called step by. And we're going to step by the block size. Oops, a daisy. What am I doing here? All right, so what I'm doing here is I've got my vector of containing my data. I'm going to return an iterator. I'm then going to use an enumerate, which creates an iterator that gives the current iteration count as well as the next value. And the next value is something that I'm just going to probably throw away, I think. And then I'm going to use step by so that I can have a custom step. So I'm not just iterating by 1, I'm going to iterate by 2,880. And so I'm looping through effectively byte by byte. Oh, here we go. That's annoying. All right, I'll just do this for now. I'm not sure if that's best practice or not, but whatever. Anyway, so that should fix that. All right, so what this is going to do is it's basically going to loop through our file. We'll loop through the vector of all the data, stepping at 2,880 bytes at a time, which means that we'll get a nice way of kind of getting a handle on a slice of that data, which is 288 bytes long when in the body of the for loop. But before we get there, we'll just sort of print out found block, and then we'll do something like that, and we'll just see what happens here, right? So let's do cargo run. Okay, so found block 0, 2880, 5760, and so on, all the way to presumably the end of the file, which is good, or at least very close to the end of the file, right? So I guess that should work. All right. Now, what I'm going to do is, so that's basically the index, right? And so we know that that we can loop through the entire the entire file this way and pull out the header and probably the data as well and the extensions and what have you, because it seems like FITS files are broken up in these these sort of chunks or blocks. I could probably call it chunk size or whatever. And then, but what we need to do is we need to look for the keyword end. And so to do that, we need to be able to pull out the data. So what we're going to do is we're going to say let header part equal fits data, and then we're going to generate a slice. So we're going to say okay, we're going to have whatever I is to I plus block size, and that should represent a slice, and then what we want to be able to do is print that. Now we're going to have a problem here, so we'll just do header, block, we'll just call it header block, and then we'll do header part. Now the problem is header part is going to be a reference to a slice. So it's a slice of our bytes basically, and that won't. Yeah. So it does. So and so that doesn't implement standard format display. So we can't use the default formatter, right? So we could. Okay. I'm guessing we could probably do something there with, I don't know. I'm not sure what that's talking about with pretty print. So again, learning Rust. Don't assume that I know everything. I virtually know nothing. So what I'm going to do is what I would normally do in another language. I'm going to basically build a function that will be able to print this. And to do that, I'm going to have to take this slice of unsigned 8-bit ints and turn that into something that printline knows how to use. And so for that, I'm going to turn this into a string. And so I'm going to create a function, and I'll just call it Stringify, and it will take some data that I want to stringify, and it's going to be a reference to a slice of these of the bytes that I care about. Okay, and then it's going to return a string. At least that's how I'm going to do it. Now I'm sure there's better ways of doing this in Rust, but I'm just going to try it this way. So let s equal, and then what I'm going to do is use the string module, and I'm going to, there's something that I've found called string from, string from, what was it? From UTF-8 lossy, and then I'll do data, and then we could just return s. You can see I'm not really writing idiomatic code yet. Oh, okay, this doesn't work. So what it's doing is it's using the string type, or string module, I guess. Is that what it is? From UTF-8 lossy does, so it converts a string of bytes, a slice of bytes to a string, and it includes the invalid characters. But what it does, if it doesn't understand what one of the characters is, it'll just use this replacement character, which will print out sort of this diamond with a question mark in it. Okay, and so this is true if we're not sure it's UTF-8, and we don't, right? We don't know. It's probably certainly not, because it's a whole bunch of binary data, and potentially anyway. But anyway, we want to be able to handle binary data as well as textual data. Now it's currently also complaining that I have a mismatched type, because I'm not returning a string. I'm returning a standard borrow copy on write. Is that what COW stands for? I guess so. Anyway, and so what I need to do here, and this took a little bit of research, is I can use this thing called into owned. And what into owned will do is it will clone the data. Basically extract the owned data and let me assign that as a value to S and return that. So that looks good. Now I think what it's complaining about here is I need to pass a reference, I presume. No. Oh gosh, I'm such an idiot. Right. So what I need to do is call Stringify here, and I could just pass a reference into that. Okay. So what I should have here now is something that will actually print the header data for me. So let's go and check that out. My cargo run again. Oh, great. So I'm basically getting a dump of the entire file by the looks of it. So let's get too long for the buffer on this thing. So welcome to the FITS processing tool built in Rust. Yada, yada, yada. Found block 0. Found block 2880. Yep, and it's still, yeah, okay. So that still looks like it's part of the header, and so on. So you can see the header actually contains quite a number of these blocks. In fact, yep, quite a few of them. So up to 17, 2080, and that's where we found the end keyword. All right. So what I'm able to do now is, because I can stringify this header part as I go, I can then use just string tools to see if we can find end. And so to do that, I'm going to do something like I'll just do this, stringify. Okay, so that's the header part, and then I'll just say, look, if the header part, and then there's something that because its header part is now a string, I can do .contains, and that's where I pass a pattern. And so I'm going to pass end surrounded by white space, and if I find end, then I'm going to say print line found the, or just say, look, found header, and then hopefully I can just break out of the for loop like this. So hopefully that will loop until it finds the keyword end, print something out to the screen so that we know that we've found the end of the header effectively, and then hopefully sort of break out of the loop. So let's try that. It looked like it worked. So we've got found header 1, 2, 3, 4, 5, 6, 7 blocks, and then we find the end keyword. Now that's great, but now what we want to do is we want to basically take we want to basically sort of suck up everything from the beginning of the file, which is where we started, through to where we found end, which is represented by this index plus 2880. And so to do that, what we'll do is we'll basically have a variable here called I don't know, primary header or something like that. We'll just call it header. Call it header primary. No, I'll just call it header HDU. And it's going to be a slice of these bytes. And I'm just going to make it equal to, excuse me, a default value for now. And so this just lets me define this this variable. And so when we find the end, what we're going to do is we're going to assign the header HDU to be a slice of fits data from the beginning to, well, it should be from I plus block size, I believe. Let's have a look. So what's that going to do? Ah, whoops. So I wonder if that's going to work or not. Cannot sign twice to an immutable variable. Great. So it needs to be immutable. Okay. What we might just do there is we'll just we'll print it again, just make sure that we're happy with what we've got, and remember it's going to be Stringify of header HDU, and this should be hopefully sort of should print out a string representation of our format. Must be a string literal. I'm not sure why that's complaining. Oh, whoops. Gosh. So we'll say header content. Yeah, you can see I'm still learning the language, right? All right, so we'll print out header content, and then we'll stringify the blob that we've just pulled out here, which is from the beginning of the file through to where we found end, and we'll print that to the screen, and we'll make sure that that looks right. Let's run that again. All right, so what have we got? Successfully read bytes, found blocks, found the end of the header, and then header content. So we've got the text blob. Okay, so that looks reasonably good. It certainly is. It's something that we would expect. And so now what we want to do is we're going to take that header data and we're just going to split it up into 80 character or 80 bytes at a time. And so we're going to do that, and then we're also going to start splitting on this equals delimiter, and then start pulling out key values. Now, now the way we want to do that, there's a bunch of different ways we could do it. I'm going to suggest that I'm just thinking, how do we want to store this? Okay, I'm just gonna comment this out for now because I think we're okay with this. Yeah, that should be okay. So what I'm going to do is I'm going to do another for loop, very similar to what I just did before, but this time I'm going to loop through the header HDU data. Okay, so I'll do the same idea, enumerate and step by, but in this case I'm going to step by the record size, and then I'm then going to sort of do so what I'm going to do here is I'm going to let record equal the header HDU data from wherever we are, I to I plus record size. Okay, and then I'm going to get a string for that, which is probably not the right way to do it, but hey, don't kill me. And then now, so we'll get a string like this, but then what I want to do is I want to match on that. Okay. Now the really easy and naive way of doing this would be to just sort of do something similar to what we did before. So we could just we could just start looping through. We just start taking each record string and we could just start splitting it. But really what we probably want to do is let's create a parse record function, and the parse record function will take our record string. Now what it will return will be a key value, right? But what I'm going to do is I'm going to create a struct to represent what a record looks like. And so to do that, I'll create it at the top here. We'll create a struct called record. Now, struct in Rust, at least as I understand it, is quite similar to a struct in other languages like C or what have you. So I'm going to create a key, and that key is going to be a string. And then within record, I'm going to have a key, which is string, and then I'm going to have a value, which is also a string. And that's the wrong syntax. Should have commas at the end. And so now this is something that we can instantiate, or at least we can create record structs, and we can start stuffing key value data into those. So we'll do that. And so what a parse record should do is probably return a record struct now. So I'll do record, which is type records, which is going to basically let record, sorry. All right, and so we haven't defined parse record, so we'll do that now. So let's do a new function here called parse record. Now, what parse record should do is take some data, which is a string, and it should return a record struct. Okay, and so what we're going to do in here is we're going to say if record contains the equals sign, then we're going to split that, and I wonder if we can just do this. I wonder if we can just do let key value equal, and I'm not sure this is going to work. Well, actually, let's see. Record split, and then what we're going to do is, so there's a bunch of different ways we can split here. And so what we're going to do here is we're going to use split n. Let's have a look where that was. Split. Please. Okay, split n. So split n is what we're going to use, and split n iterates over substrings separated by a pattern restricted to returning at most n items. So I don't think we care about the case where we have multiple equals signs, but we want to have, if that's a possible thing in a fits file, then we'll cater for that. So we'll only effectively split on the first equals, because I hope that's what it's going to do, because we'll just return two matches. And so in this case, we'll look for that, and then this is going to be an iterator, and then we want to call collect, I think, and we'll see what blows up. Probably everything. Expected struct record. Oh, well, that's fine. Expected. Okay. Got itself pretty confused. Let's actually, I'm probably making lots of mistakes, so let's see what happens here. Expected struct record. If record contains equals, then do something. Let the key value equal. So what does split n return? It returns, okay, what does collect do? A collection. Turn one collection into another. I'm guessing that I can't just do this, because what I was hoping I could do is something like this. Just basically define these two variables, key and value, that are basically string slices, and stuff them into a record. Yeah. I'm sure this is wrong. And then the idea would be that we do r.key is equal to key, r.value is equal to value, and then you return r. But that's clearly not right. Yeah, it doesn't seem to like that at all. All right. What's this complaining about? Let's see. Default is not implemented for type record. Good call. I wonder, yeah. So I'm going to do something like this. Value. So I think the problem is this this split n isn't doing what I expect it to do, and also I don't really know what I'm doing. So anyway, what I'll do is I'll see if there's a better way to do that. But actually, let's cheat. Let's just have a look at what split n can do for us. So Rust split n. Okay. Will it do what I want? Probably not. Show declaration. I want an example. So Rust split n example. That doesn't help. Let's see what this thing does. Split n entry. Parts. Whatever parts is. Vector. Really? That's a bit annoying. Anyway, all right. Well, okay. So what I'll do is I'll say let records. This just seems crazy, doesn't it? Anyway, I'll do it this way. So we'll do a vector of string slices, and we'll say that equals to record split 2 equals, and then collect, and then I'll say actually that's probably only if that split n, sorry, split n. Just want to try and get rid of the errors. All right, so this should kind of work. So if record contains equals, then we create a new vector of string slices, and we split on the equals and only return 2 parts, and then we collect them all together, and then we have this new records variable here, and then we could do something like let r equals, well, r is a record, and we could say that key is equal to records 0, and value records 1. Okay. Right. How do you do a literal struct in Rust? Okay. Literal struct Rust. Defining and instantiating structs. Let user blah blah blah. Okay. Go. What's complaining about here? Expected struct string found that. Do I need to stringify? I hope I don't. That would be silly. Or maybe I could just do, maybe there's like a toString or something. Or, sorry, toString. Please let there be a toString. to string. Else return records. Oh, I mean, well, actually, what I want here really is an option. So I'll do it this way, and then I'll say else return, hopefully none or something like that. Else return. Expected that. Found struct. Some are. Okay. All right. So let's see. I don't know if this works. So anyway, we're going to parse the record. We're going to now return an option because we'll sometimes find a record that contains equals and sometimes we won't, in which case we will return none. And what we did here was we were basically splitting on equals, returning two parts, putting in a vector, creating a record struct with the key equal to the first part and the value equal to the second part, converting that to string because we defined the struct as having a key and value of type string. Now parse record now returns an option, and so I guess the option will need to let's have a look. We'll need to match on or something. We'll need to destructure. All right, so we'll just do something like this. We'll go match parse record string and then we'll say if we got something, which should be some records, which is key value, then do something, and if we got nothing, then I don't know what we'll do. We'll do nothing for now. I don't know what we do in the case where we get none. Let's maybe print didn't find a sensible record, and then we'll just we'll leave it like that. Okay, so and so what we're doing here is we're destructuring the record, and we're saying that if we get something, then we'll basically be able to pull the key and the value out, and so we'll just print that for now. So I'll do print line, and I'll do I don't know. Let's just do value. So this will be key and value. Cool. So that should actually work now, hopefully. So we're now going through and we're looking at all the data and we're stepping by block size. We're finding end. When we find end, we're pulling out the data into a slice, calling it header HDU. Then we're stepping through the header by record size, which is 80 bytes at a time or 80 characters at a time. And then we're getting a slice of the data, calling it record, turning it into a string, parsing it, pulling out the key and value and just printing them. And if we don't find a key value or an equal delimiter, then we're just printing something. And the parse record, which took a long time because I'm a complete newbie at Rust, effectively just does the same thing. And so we could have just put that up in there, but whatever. We'll keep it out as a separate function. It basically uses split n, puts it into a vector, and then builds a record struct and returns it. So I think that should be something that works. let's try. Okay, so I didn't find a bunch of sensible records. It found a whole bunch of key values, which is encouraging. Oh, there's heaps of white space. We can maybe trim that. But it sort of looks like it's doing what we wanted it to do, which is kind of encouraging. I don't think we need this this print line here. Maybe we do. I'll just comment it out for now. But yeah, this just doesn't look very clean. It doesn't feel right, but whatever. It sort of works, doesn't it? So what I'll do though is I will see if I can use a trim function on the string. I don't know if that's something that I can do. Do I trim a string or do I guess so. Do I trim? No. Is there a trim here? Trim. Yeah, I just basically want to be able to take the slice, because this is a string slice, right? And then I want to trim it before I turn it into a string, just to get rid of white space on either side. Now this should hopefully trim both leading and trailing, which it does, so that's good. Okay, whoops. All right, now let's try that again. If I can use the right command to save my buffer. Okay, that looks a bit better. Anyway, so we've got rid of bunch of the white space, which looks good. Okay, now the last thing that we want to do here, just before we finish this video, because it's going long, is we want to store this somewhere. And now a nice way of storing that, generally speaking, would be to use something like a hash map. So something that gives us pretty constant time to look up a value given a key. And so what we will try to do is we'll try and use a hash map. Now, there is a library, I believe, called hashmap, which is part of the standard collections library or something like that. So Rust hashmap. Okay. So, yeah. So we need to import it. We use it this way. We create a new hash map, and then we can just do insert with, I guess, key and value. And then when we look it up, we can do contains key, look up by key. We can remove. Nice. We can just do get for a particular key. Okay. Anyway, all right. So we'll use a hash map for now. So what I'll do is I'll go back up and I'll import it. So use standard collections hash map, and then down in here we'll create a new hash map. So we'll say so I will have a new variable here that I call header records, and I will create a new hash map, and then I will, oh gosh, what's wrong with that? Doesn't seem to know about hash map. I don't know. What we're going to do here is we'll print it still, but then we'll also stick it inside of our hash map here. So we'll do what was it? Hash map, header records dot inserts or something, and then we'll do key and value. that should be pretty straightforward. Cannot borrow. Aha. Mutability. So we want a mutable variable there. All right, let's see if that runs. Okay, so it compiled and ran. Now I guess what we could try and do is we could do something to find out how many headers we found. So we'll do number of header records. And then we'll do, well, can we just get the number of keys or something like that? I don't know. What did hashmap give us in that regard? Let's have a look. Is it as simple as doing something like header records length or something? Don't know. Let's see. So what does that return? A U size. Sounds promising. All right, so let's try running our program one more time. So we found 211 header records. I'm guessing that's probably okay, and these are header records that were split with equal delimiters. All right, so if we go back to our example, to our data file here, you can see we have a whole bunch of data, probably 211 records. I'm guessing that the non-equal delimited ones were probably these. Remember, we're reading 80 characters at a time, and it was probably a whole bunch of white space that we were splitting on, or reading and then trying to split on. And so I think that's it, right? So I think what we've done, and you've seen just what a newbie I am when it comes to Rust, but I think what we've been able to do today is take our very simple Rust program that just opens and reads files, start stepping through the fits file according to the structure that we understood very quickly from the PDF. And I'll link a link to the PDF below as well. And then start. We've done some really basic things like turned these slices into strings and used string functions or methods like contains to look for, start sort of parsing, and I use the word parsing very liberally there, the header data. Store that, basically use that as a way of stepping through and looking for the records inside the header, looking for key value pairs, parsing again, loosely using the term parsing there, and then storing that in a hashmap. And that's kind of pretty common. It's probably not idiomatic Rust, but we do actually have something now that we could use. And in fact, what I'll do is I'll just clean up the program a little bit. So I'll just we won't print that. We will. What output do we provide? We don't need all this output, right? So we've found the header, the number of header records. We'll keep printing that for now, and we've printed how many bytes we've successfully read, and I've misspelt successfully, so we'll fix that. And so this is all already immediately useful. Maybe what we can do is, I think, in the next video, what we'll start doing is we'll do something similar with this next data unit, but this looks like it's just binary data. And so we'll need to go back to the spec and sort of understand that in more detail, because goodness knows what this is, right? It's a bunch of bytes, but how do we interpret it? And I suspect we're going to have to use the header information that we've just parsed to interpret that. I mean, the fact that it's talking about 32-bit floating point numbers here, I don't know if this means it's probably signed or something as well. So it looks like fits is flexible enough that allows us to specify the number of dimensions in the data set. Maybe this is the dimensions for the different axes. It did say that it could have up to, I think, was it 999 or 1,000 dimensions in the data, which is kind of pretty crazy. So this looks like it's probably two-dimensional data with 2,000 by 4. And then this is probably something to do with how we interpret the binary data as 32-bit floating point numbers. But we'll need to know how to interpret that. And so in the next video, we'll certainly be using the header information, I suspect, going back through our fits spec, and then we'll write another block of code that can help us start interpreting the data. And then hopefully, if the data is image data, then we might even be able to start displaying that. But I think that might be ambitious. So let's say for the next one we'll start parsing the data, and then maybe the video after that we'll start trying to display it if it's image data, which I hope it is. Okay, so look, that's been a pretty long video. I'm still learning, and look, I did have some private comments about previous videos, some helpful comments about how to write more idiomatic Rust. So please keep that coming. I'm definitely trying to learn. I did buy a couple of books. I bought the O'Reilly book, Programming Rust, and realized just how little I actually know about Rust, which is great. And please stay for the journey. I'm looking to kind of build this up over maybe sort of 10 or 15 videos. I don't know how long it'll go, but we'll end up with something that's kind of useful and hopefully pretty cool. So again, thanks for watching. Please subscribe if you find this interesting, and please come along for the journey, and I'll see you in the next one.